Normally, we have the structure of carbons. With the carbon here, and then it repeats in space, and so on and so forth. We have a lot of carbons. What's called NB center is when we have one nitrogen atom, and nitrogen, remember, in the periodic table is in the group 5, so it's a different group actually from carbon. So this type of defects by itself, so substitution of nitrogen, but very often it's actually energetically preferable when you have a vacancy. So carbon lattice structures to have a vacancy nearby, and we have what's called nitrogen vacancy center. So diamond lattice, but from time to time you have a nitrogen and nearby a vacancy. And in particular, very often, very interesting properties we have for NB minus center. So we have extra electrons there. And we'll talk about it. So to compensate for electrons, if you have negative centers, you must have something positive in the diamond. And normally it's just nitrogen plus. Also, instead of carbon, you have nitrogen. Also, this does not have extra electrons, so it's in a fixed group nitrogen, but it gave up the electron. No radicals, no extra electrons, everything normal for bonds formed like carbon. You also quite often have these centers as well. When you have not N plus, but you still have that electron, so it's just neutral nitrogen, but you have an electron. It is P1 half, so we call it P1 center. But yeah, very interesting properties are in this type of NB centers, and we're going to focus on them today. So how to consider them from the group theory perspective? First, we need to consider in general, we need to explain the problem. Once again, we have 3 carbons. Each carbon usually provides 1 electron to the bond, to the normal bond, if it was carbon there. But now we don't have that carbon. So we're going to call this dangling bond. The dangling bonds, and nitrogen actually in its dangling bond has 2 pairs of electrons, right? So it provides 3 bonds, 1 electron per each bond, and 2 are paired on this orbital. So together it forms this kind of tetrahedral. It's actually not tetrahedral, so it's like a pyramidal structure, which is clearly C3D, right? And idea with the X is C3. So all the properties. So let's write down what symmetry iterations we have in the C3D. We have the nothing iteration, 2 C3, and 3 sigma D, which is mirror plane going through the bond. And then we add extra electrons. That's what NB center is. Here we have the reducible representations A, B, E. And we fill up the character table. 1, 1, 1, fully symmetric. 1, 1, minus 1. And 2, minus 1, 0. Okay, that's what we're going to use today. So yeah, what's the purpose of this whole exercise? The purpose is to derive and to understand how electronic structure will look like, where the electrons are going to be located. So in total, how many electrons do we have? 1, 2, 3, 4, 5, 6 electrons. 6 electrons. So we have 1, 2, 3, 4 bonds, 4 participating atoms. So these 4 bonds for molecular orbitals, eventually we'll find combinations of them. We need to decide how to put 6 electrons on them, right? It means that in the whole structure here, we have 1 electron coming from each of the carbon atoms, 2 electrons coming from nitrogen, and extra electron coming from somewhere in the crystal. So yeah, by the way, so in this whole crystal structure, you always have also NV neutral. Nitrogen vacancy, but no charge. So this is all vacancy, carbon, but no charge. So that's what I mean. Apart from NV minus, you have all sorts of other vacancies in diamond. We only consider NV minus today. It's very interesting for reasons which may become clear later. So let's call these Dangling bonds. Let's put this electron here and say that. So this is, we call them dangling bonds. How are we going to call them? Let's use phi. So phi I, where I is 1, 2, 3. We label them 1, 2, 3. And this orbital, so these orbitals, we label phi I, phi 1, phi 2, phi 3. This is orbital for nitrogen, phi nitrogen. So what's clear from the beginning? So originally we have some, obviously before we do anything with group theory, we just have each of these atomic orbitals equal in energy, right? So we'll have this phi 1, phi 2, phi 3 somewhere in energy. It's carbon. So then we have also nitrogen energy. I think so nitrogen itself is a larger nuclear positive charge, which attracts electrons a little stronger. So probably it's reasonable to assume nitrogen orbital by itself lies a little lower in energy. But it's not even that important actually, how they lie before. So and what we're gonna do in the whole exercise. That's actually a questionable statement. I don't know, to be very honest. Maybe it's not, but I think it's lower because what's clear, for example, if you take atoms by themselves in the second row of the periodic table, in the second tier, you go from lithium, beryllium, you go further, bore, carbon, nitrogen. So atomic radius becomes smaller and smaller. That's clear. Yeah. So this is not the same necessarily here. It's already inside the structure, but I assume it's a little lower than it. It's actually counterintuitive. It's not classical physics, but it's quantum physics. Indeed, like fluorine, the smallest atom in the material, fluorine, despite its 7 electrons, they have a repulsion actually, but charge puts them still kind of closer. No, it changes charge +1, +1, +1, +1. Nuclear radius doesn't change. Oh, well, for our purpose, nucleus is just a point charge. Yeah. So, with group theory, we should understand what's the electronic structure should look like. Okay, so also we need to define, how do we start? So first we know that we need to group these atomic orbitals into groups within which they can interchange after symmetry activity. So obviously nitrogen orbital forms its own group. Nitrogen will never become carbon, no matter what you do in C3V. And you have 3 carbon orbitals that can interchange. So remember, let's do this exercise again. We take nitrogen, let's say start with nitrogen. We take its orbital and let's repeat this symmetry operation, but now we distinguish technically each operation. Not just taking the class, but we distinguish, for example, rotation clockwise, anti-clockwise. And let's do whatever you do in this group with nitrogen, with this bond, it will stay nitrogen. So what's clear, it transforms under which the reduced representation. Right? A. So we write it basically this A. If we were to check, does it transform under B, you have here -1 for this. And when you sum them up, it will be 0. The same here, it goes with 2, -1, -1, 0. So only with A, some of them gives something non-zero, we normalize it, it's just there. So now repeat the same thing, let's say with the first. At first, let's actually decompose. So we take the whole group, all 3 of them, and let's see as a group, how do they transform? First, we do, so let's do the whole group, I. So epsilon, do not an operation. All 3 orbitals stay in their positions. They contribute to the character S3. You rotate it either clockwise or anti-clockwise. None of them stay in their position. 0. Sigma V. For these 3 orbitals, obviously one of them will stay, 2 that will stay, there is 1. So that's the character line corresponding to the reducible presentation. Now we can decompose this line into some other lines corresponding to irreducible representation. So do you see clearly how to sum up any of these rows to achieve this row? How can we do this? E and A. E and A. Nice. Can you already tell me how they look like? Actually, we did this exercise for ammonia, but we can repeat it here as well, right? So how to find which combination is E and which combination is A. We do it like this. First, this should be E plus A. Let's take first orbital first. And let's run the whole set of iterations, taking into account each iteration, not just the class. So when we do Phi1, we have an iteration Phi1, rotate clockwise, it becomes Phi2, rotate anti-clockwise, 3. And we do it first with all positives. A, right? P3V, one of them will stay in this position, another changes. So you sum them up now, 1 plus 1, 2, 3, 1, 2, 3, and normalize. Normalize such that square of each coefficient, sum of squares equal to 1. So what we did right now, we found combination that transforms under A. This is, and now let's do the same, but take into account coefficients for the character line E. So here we'll have 2, here we'll have minus, here we'll have zeros. And we normalize, now we sum them up and we normalize. So 4 plus 1 plus 1, 6, so it will be 1 square root of 6 2 C1 minus C2 minus C2. So this is one of the orbitals, one of the combinations of atomic orbitals that transforms under E. But we know that this is degenerate, so it's a two-dimensional representation. There should be a second combination. And that combination can be found through orthogonality condition with both of these orbitals. And we already did this exercise. We just write down some combination C1 plus C2 plus C3. Then you do, basically Ketten-Brush multiplication. And you will find that it should be 2 minus 1. So these two orbitals transform under E and this transform under A. Okay. Let's go probably there. Such that we can still keep that. Now, what do we do now? Now we can, so we decided, we found that nitrogen transforms under A. Then we have 3 orbitals composed of combinations of carbon. We call them P1, which is also fully symmetric combination, which transforms also under A. So that means these molecular orbitals can interact with each other, and they will produce non-zero interaction. And the second and third combination they will not interact with nitrogen. They're different symmetry. They form separate group by itself. They degenerate, transform under E. So remember, so what now we need to do? We need to find the Hückel determinant. So we need to agree with each other about some terminology here. Let's say nitrogen will interact with itself, and I already have some notes, the way I labeled them before. Let's use the same terminology. So let's call it some energy nu for nitrogen. So that's actually basically this. Where nitrogen is sitting, right? By itself before interaction. Then let's say this is carbon, each carbon with itself. Let's call it new carbon. That's pretty much what your carbons is sitting. And as I said before, I assume, first of all, I assume both of these numbers are negative. But I also assume that nitrogen is still a little smaller than carbon. It's my assumption. Negative there because we compare everything with free electrons unbound to the atom. So when we have atom, it stabilizes it. So both. And then let's use this terminology. Whenever each of the carbons interact with nitrogen, we're gonna call it. Well, I think this is something that's not that important. But at the end of the day, you will see that what's important actually to understand some values of these parameters to, let's say you have a situation when you have a degenerate orbital, 2 orbitals, and another orbital, and the question is which one is lower, which one is higher. Actually, that may become very important. But I think even without doing extra calculations, you can kind of logically make good assumptions. But we also should assume, because this is real world, we need to assume how carbons interact as well, because they're nearby. They actually also form in this kind of, they can overlap, right? Wave function, so they can have some contribution, and we're gonna call it HC. So once again, I assume all of these things are negative. And potentially, I think HC, I would assume less than HM. Because carbons are just simply closer to each other. Oh, well, that's actually questionable. Questionable statement, but yeah, let's see if that's important. Well, here, look, there was supposed to be another carbon here. We took it out, it's vacancy. So, yeah, actually, I don't know. Yeah, let's maybe not do this assumption. Let's see if it's going to be important at all. So, Kukil determinant. So, what do we need to write down? We need to write down Kukil determinant.
Yeah.
So,
just so I can figure out the wave function. Now we want to figure out the answer.
Yeah.
So that
So now we remember, if all of these orbitals had its own symmetry, we would just make a matrix 4 by 4 in which we have only diagonal elements. But now two of them have the same symmetry, so we need to consider their interaction. So Kukil determinant should look originally, let's say, nitrogen minus E on the diagonal. Then we have what nitrogen interacting with first, well, with the wave function, which has the same symmetry, which is this one. Then you have the same element again, because they're real. There's no difference in which order I write this. And here we're gonna have first orbital interacting with itself. So this is first block 2 by 2, which belongs to the fully symmetric functions. And then you have two blocks 1 by 1. And it's going to be a little small, where you have second interacting with itself, and the third wave function interacting with itself. And zeros everywhere. So yeah, we need to solve the determinant, and now it's block diagonal form. So we separately we can separately focus on this 2 by 2 determinant and then this 2. Right? So let's find out. So when we say nitrogen, so it's already new M. We already, that's how we call it.
Second row and first column of this. Shouldn't that be like 5 on psi n? No, the one like there not be psi 1 h 5 1 phi n.
No, look,
Psi 1.
this one, that one. So from 3 individual atomic orbitals,
Yeah.
for dangling carbon bonds,
Yeah.
we found symmetrized combinations. And now we check based on group theory who can interact with who. So only psi 1 can interact with phi n. So that's why we have non-diagonal here. Yeah.
What I'm saying is the order of the Kenton
this
the Kenton bra should be
technically should be actually here should be different. if mu n on the left, but it doesn't matter because they're not complex. They're real in our case. But yeah, fundamentally more proper to write psi one and here. Or vice versa. So okay, we found that. So what about this? N H exactly psi one. Now it's a little interesting. So psi one, let's write it in explicit form. So the coefficient 1/3 comes out. Then you have I n H P1 plus 2 plus 2 3. So what is going to happen? So each of these combinations, phi n, phi 1, phi n, phi 2, they give this, right? We call it Hn. So interaction energy between nitrogen and carbon. And 3 of them divided by square root of 3, so it's a third of 3 Hn. Right? All right, what about further? What's this? What's next? Phi 2, phi 2. Let's find phi 2, phi 2. Phi 2, phi 2, I mean. And technically, because they're degenerate, this should be the same as psi 3. Psi 3, but let's check. So psi 2, psi 2. Okay. Let's write down in explicit form. 1 square root of 6 twice is 1/6. Okay, I'm not gonna write this. You can do this step in your head. So let's do it. This H is the same. Psi 1, psi 1. 2 times 2 is 4. 1, 1, psi 1, psi 1, psi 1 gives this, right? Wait. 1, 1 is gives you, yeah, we call it VC. Then psi 2 will give you VC. Phi 3 will give you VC. Now we take cross terms. Actually, I chose the wrong orbital to start with, but let's do it. This one would be my simpler one. But let's do it. So 2, and we'll go with minus. Minus 2, phi 1, phi 2 gives you, we call it HC. Then we go phi 1, phi 3, which gives you 2HC again. And then 2 goes with 1, 3. So we should be, well, we took it minus 2, minus 2. Yeah, should be just 2HC. Thanks. Let's just double check this. This is my symbol. So the 2 VC and 5 minus 2 HC. Yeah. So it should give you VC minus HC. So it should give you the same here. 4, 6 minus 6. Yeah, divided by 6. Okay, so what we can do right away, we can say that when we do this analysis, so this is your VC minus HC. HC is also negative, so VC combination, 2 of these orbitals raise up a little bit by the value of HC. And this we call E orbitals. Two degenerate orbitals that transform under E. But to find out what's happening with this, we first also need to find basically solve the determinant, right? There is no other way, but we haven't found psi1, psi1. So we have what? 1/3. 1/3, and then each we do this Hückel determinant, Hückel iterator, psi1, psi2, psi1, psi3, give you, you're gonna have 3, we call it DC, plus 6, because each gives 2 interactions, we call it HC. So really DC plus HC plus 2 HC. Clear, right? You just do this, the same thing. I was skipping this step. Oh, in red and did this in my head. So we have to take this HP1, this HP2, repeat it for this. So let's solve it. So we have to do this. How do you solve the determinant? So we have determinant un minus E. Here we have square root 3 H n with 3 H n. And here we have VE plus 2 HT minus E equal to 0. Shall we do this? You remember how to do that? So we have V and let me just double check if there's no mistakes. And C plus 2 HC. Okay, looks like something correct. Minus 3 HM equal to 0. Eventually, we're going to have a quadratic equation. It looks like you have to follow it if you really want to find any. So minus E goes C plus 2H minus N. Sorry?
Is it 3 minus 3 times 4?
Indeed, right? Indeed. So and then we have V and VC plus V and VC plus 2 V and VC minus 3 H squared equal to 0. How do we solve for the equation? So if we have ax squared plus bx plus c equal to 0, how do we find x1? I always forget. It's minus b plus minus square root, so it's 1/2. B squared minus 4ac, right? Shall we solve it or shall we let's do it quickly. So what I can delete. I'm probably actually let's try and use still going. Okay, so let's do it. What is A? A in our case. Just one, good. B in our case.
Minus.
This.
Minus.
It's minus.
So if I have PC, let's see.
And C is once again. Can we do something with C? Because
Just all C maybe.
the N the C plus 2 N is E minus 3 H N squared. Okay, that's good. So let's find what's gonna be B squared minus 4AC. B squared, so BC plus 2HT plus VN squared minus. Let's actually take still VN out of here. Or we can BC plus 2HT is kind of feels nice to put that together. Minus 12, a minus gives plus 12 HN squared, right? And I think what's clear now let's try to open this first bracket. But let's open it smartly. So let's keep BC plus 2HC together, squared. So you're gonna have plus VN squared, right? Plus 2 VN times VT plus 2 HC. And then look, so nice. And now it takes minus 4 VN. You keep the same thing. Plus 12 HN squared. And now what I will do, look, this was 2 VN VC plus 2HC minus 4 VN VC plus 2HC. So I'm gonna use advantage of the board, not just to minus here. Right? And then I put it back into the square. So, but now it's a square with a minus. We're gonna have VC plus 2HC minus VM squared plus 12 HN squared. Okay. All right, so what we're gonna have here, minus D plus minus square root. So our energy solutions are 1/2 minus B. B is already negative, so we have BC plus 2HC plus VN plus minus delta. And where delta is square root of BC plus 2hc minus En squared plus 12hn. So some expression, but at least you see by analyzing relative values, you can kind of have an estimate where exactly in energy they're gonna go. So two of these orbitals, they said raised up a little bit. But here you have, depending on the magnitude of interaction hc, but you're gonna have some combination which is positive, lowers down energy significantly. And we call it A, because it transforms, we know, under A. And we have A star. So if we were to draw, so let's draw.
This is the mixed state, right?
So now it's the mix. So let's make a drawing, maybe here, how these orbitals actually should look like. Schematically based on Q. So first A combination. We have all three dangling bonds coming with positive sign, and nitrogen bond coming also from positive sign. Obviously, this is your combination which is bonding. Now you have antibonding combination. And also, I haven't even found, so far we talk about energies. If you really want to find how exactly your wave functions look like, with which coefficient. So you have to put these energies back into your Hamiltonian, into the determinant, and find coefficients in front of eigenvectors. So you can find these eigenvectors. But it's going to be some form of, let's call C1 times Pn plus C2 times psi1. So that's your combination with positive. And second combination will have the same coefficient C1 Pn, but then minus C2 psi1. And the only condition that I know for sure is C1 squared plus C2 squared. They're normalized. But exactly how they look like, let's not do it. If you're really interested, you can put it. We did it once before. So you put that energy one back into this determinant, back into here. And now we have C1, C2, it's a vector, and you find it. But it's obviously going to look like this. So you have now nitrogen positive, 3 carbons in negative. So this is anti-bonding combination. So that's why we have a star. And E combination. We don't have nitrogen participated here at all. This combination is made of your carbons. This has like little bigger first atom, let's say. It's positive, this two negative. And the second, this first carbon also doesn't participate. Just second is positive, third is negative. Right? That's what we found. Psi2, Psi3. This is our Psi2. This is our Psi3. So that's how they look like. So now we found more or less energy structure. And that's it's indeed like this. So A star is not above E. Yeah.
The previous picture was electron density.
It's just basically it will reflect electron density once we put our electrons on these orbitals. Let's do that now. Some of them will pair up, some of them not. So we have 6 electrons, right? We discussed. So we put this two here, two here. And now 1, 2, 3, 4, 5, 6. You see, they're unpaired because they're occupying degenerate orbitals, and by Hund's rule, lower energy is triplet. So now we found where electrons are sitting. Indeed, electrons are sitting. So now let's find spin density, not just electron, because again, electron here is there, two electrons are there, but they're paired up. They're forming the shells that they're not participating, like atomic shells, like S1. But what's important here, let's find spin density. So spin density is indeed determined by your psi 2 and psi 3. Maybe let's keep that, maybe it's useful. And here we come. So you have density of electron on the first atom. So we need to sum up square of the coefficients of psi 2 and psi 3. So for psi 2 on the first atom, first coefficient squared is 4 divided by 6. On the second orbital of psi 3, there's no, so P1 does not participate, so it's 2/3. If we take the second atom, we take 1/6 coefficient in front of P2 plus square of this here, 1, 2, also 2/3. And the same is on the third atom. Oh, by the way, you notice that here, it almost, we have some preference. If you look here, right, why is P1 bigger than P2 and P3? And not P2 bigger than P3? Technically, you can do the same, but if you choose P2, P2 minus P3 minus, then here they switch. Okay? So it's always, the choice is yours, the choice which orbital to start with here is yours. Depends on the labeling. So what we found indeed is kind of interesting. So it turns out that in the MV center, basically unpaired electrons, there are two unpaired electrons, and they're not on nitrogen in the ground state. Based on this electronic configuration, you can say that electrons like flying, these two unpaired electrons, they're occupying carbons. They're no nitrogen density. That's why actually their hyperfine coupling to nitrogen is very low in the ground state. Because basically there is no electron density present in the nitrogen nucleus. But now what's interesting is what happens if you shine a light.
Did you say hyperfine?
Yeah. It is interaction between electron and nuclei. So
this hyperfine interactions that we typically, the splitting that cause.
typically what?
The hyperfine splitting that happens, the same effect.
Yeah, hyperfine splitting, exactly, is hyperfine interaction. So it is mainly for light atoms, it is mainly determined by Fermi contact interaction, which is basically how much electron density you have in the center of the nucleus. In this, not in the center, in the nucleus, on the side of the nucleus. So it's actually non-zero probability of electrons to be there and field the field. At least that's how the theory works. A little bit. A little bit.
Very significant. For example,
Are you talking about ground state or excited state? Let's talk about excited state first. So what is excited state? It means if you shine light on this system, some sort of green light, maybe 530-ish nanometers or something. So what will happen? You have the same electronic structure, but you can think what type of transitions may happen. So I think you can realize that one of the electrons can jump from here to there. So now you have one of the orbitals fully paired electrons and one of these unpaired. So that's what happens when you shine light. And then now you can talk about, okay, and what's the actual electron density in this situation? Now you have one electron sitting on basically on a orbital, on a antibonded orbital, and we agreed that we don't know coefficients, but let's say there's like equal 1 square root 2, for example. So it means that the electron is going to sit on this sort of, so it will be present both on nitrogen and on carbon, right? So this ground state. And this is excited state. So in the excited state, electrons are going to be everywhere on each atom. So they're going to be more spread out in space. Therefore, maybe their average distance between them will be a little larger. And what's important that you have now non-zero probability of electron to be on the nitrogen. So it's going to be much larger. So that's what I know from literature in the centers, that in the excited state you have large hyperfine capsule to nitrogen, but not in the ground state. But now so that's what actually what motivated me to start looking at this whole Hückel picture of the NV center is to understand this diagram that people always draw for energy levels in NV centers. And so far we drew on the electronic configuration to really find terms. Remember, specific states with specific energy, which are responsible for actual frequencies of transitions. We need to now do a little bit more group theory. And that's there are a few tricks here. So what are we going to do? We're going to maybe we need to keep. So if you guys, maybe you can make pictures of the pages and we can safely delete it. Okay, let's delete this one. And I think what we're gonna be using also this line. Let's just delete this one. So what we need to find is term, and terms are determined by also product of irreducible representations responsible for the orbitals which contain unpaired electrons. For example, this is very simple. So this electron, let's start with the excited state. It's actually a simpler situation. So we have one electron on the orbital that transforms under A, and one electron, unpaired electron, that is on the orbital which transforms under E. So what we need to do to find the term responsible for this state terms, we just multiply lines corresponding to A and E, and it's going to be just E. So 2 minus 1, 0. So this combination clearly is simply E, right? So it means that term corresponding to the excited state can be E, either triplet when two electrons are in a triplet state, or singlet. So there are two options. And we know that the triplet state should be lower in energy because of Hund's rule. All right. Now let's talk about this. So here it's a little bit more tricky because we multiply E by E. So what are we gonna have? 2 times 2, 4. Minus 1 times minus 1, 1. 0 times 0, 0. How do we decompose that? Do you see already? Actually, is it even called EB? I just put it out of my head. It's called A1, A2 actually. Guys, we're doing this group theory for the whole hour and it's actually wrong terminology. Let's use correct terminology. They usually call it A1, A2. What? It's just a letter. No, it's open C3D group. In C3D, you can Google it. Does it call it E or E1, E2? Yeah, they call it A1 and 2. I don't really remember what's the real rules, how to distinguish. It's usually determined by with respect to the sign plus or minus for the specific operation. So probably for C3, if for C3 is the same, you cannot call it B, it's A, but probably for sigma V. So I never remember the details. You just go open the character table and see how they're named, because it's just the convention. If nothing would change if we call it B. But what's the convention is because later people use this terminology. So therefore I need to rename it A1, A1, everywhere here. A1. So far we didn't encounter B, so let's yeah. But now look, I think this line is the same as A1 plus A2 plus B. Is it correct? Right? And now we have a little problem. So normally, so we have this basically situation, 2 electrons occupying 2 orbitals. In general, so we have a Pauli principle, which doesn't permit us to have 2 electrons pointing up on the same orbital. So how many states in total we may have? This can be found through binomial coefficients. So we have 4 positions on each orbital, 1, 2, 1, 2, and only 2 electrons. So that's how you find how many combinations, which is what? 4 factorial, 2 factorial, 2 factorial would be 6. But if we use the same simple principle here, we say, okay, we have A1, A2, E, there must be triplet states, and there also must be singlet states. We probably overcount, so which means we have 3 plus 3 plus 3 times 2, 6. Plus 1 plus 1 plus 2. So we have what, 6 16. Is that right? Yeah, 16, too much. So some of them are not real if we take into account power principle. And there is a trick how to do that. And it's all about, again, Pauli principle. Actually, if we have a combination, we normally decompose full wave function, which is both spin and orbital part. We decompose it into combination. So for triplet, we should have electron state in this either of these states times, so any of that times some orbital part. And according to Pauli principle, if your spin is triplet state, this is symmetric with respect to permutation of two particles. So this has to be antisymmetric. And vice versa, if we have a singlet, which is antisymmetric, that should multiply with the orbital part, which is symmetric. And there is a way to deal with that. And there's a formula. So formula is like this. To find the symmetric combination, where are we going to draw it? Yeah. And I'm not gonna explain where this comes from, but actually it's quite logical if you really think about it. So to find, let's say you have some irreducible representation when you find this product, direct product, and you want to find which one of them corresponds to symmetric and which one corresponds to antisymmetric. So the rule is like this: you take a square of the symmetry operation to find the line of the characters, and take a plus for symmetric and minus for antisymmetric, and do the character of the square of the operation itself divided by 2. So what does it mean? Let's find, for simplicity, square of the operation line here. So square of the operation, and let's find character of the operation square. So square of the operation for E times E, very simple. You take this square 4, this square 1, this square is 0. Now you take character of the operation square. E, you repeat this. E, so character of E is 2. When you repeat C3 twice, it's another C3.
Yeah.
Character of it is -1. You repeat CV twice, it's E. Character of E is 2. Okay. So now we find, let's find the line. So this line actually should be a sum of symmetric and non-symmetric part. Let's check. I have to redraw it again. So again, E times E symmetric. And we're gonna have E 2C3 3. So what we do?
Why was the character of 3 sigma b squared 2?
Because sigma v squared is E.
Yeah.
Character of E in this character of E is 2.
Character Z.
So let's do. So here we first take symmetric part. So we sum them up and divide by 2. 4 plus 2, 6 divided by 2, 3. 1 plus minus 1, 0. 0 plus 2 divided by 2, 1. Okay, we found this line. What is this line? You can clearly see it's A1 plus E, right? And if we take E times E antisymmetric part, we do minus 4 minus 2, 2 divided by 2, 1. 1 minus minus 1, 2, 1. 0 minus 2, minus 2 divided by 2, minus 1. Indeed, everything worked out. This is A2. So once again, if you don't take into account this symmetry, you just take E times E, you have a line 4, 1, 0, which is indeed can be decomposed into this. Count as 4, 1, 0. But now with this formula, we decompose it even further. So now we know that we're coming back to this. Only symmetric orbital state can correspond to the antisymmetric, which is singlet electronic spin state. Therefore, there cannot be triplet for these states. There cannot be triplet here. There cannot be triplet here, and there cannot be triplet here. And since this is antisymmetric orbital state, there cannot be singlet for this state. Okay. Now let's count their multiplicity. So this is one-dimensional representation, 1 times 3. So this is 3. 3 plus 1 plus 2, indeed, this goes to 6. Now we could match, right? So what does it mean? Now we know we can draw a nice energy level structure. Probably we're going to do it here. So now we're talking about actual terms, actually states with the specific energy. So the lowest state in the ground state is the state with the maximum spin according to the Hooke's rule, which is A2, 3. Now it becomes familiar. Then we have other states, and that actually not trivial which one is lower, which one is higher. And I'm not going to lie that it's easy to understand, which you have to do more specific calculation for that. But I know from other people, from papers, that actually E1 is a little lower than A11. So that's your ground state. And then you have your excited state, which is actually even higher in energy. And also the triplet is going to be lower among them. So we put E3 here, and then E1 here. And again, specific positions are not clearly defined. So normally what happens, people, when they draw this energy diagram state, differentiate. On the left, they keep the triplet state, on the right, they put excited state, singlet state. So we're gonna do the same here. So we do this A11, E1. And here it is E1. So we remove this from here. So that's general picture for the diamond. And actually, in reality, some of these very high energy states may not even be accessible. Something may happen with uranium center or ionized, they say it's never going to be even reached. But normally, when that's the whole reason for this exercise. When you go to conferences and you see these diagrams, people say that you have a ground state, then you shine light somewhere, and you go into the excited state, then you have intersystem crossing. You may have some also actually fluorescence and much lower energy. And then you may have some also non-radiated transitions back. So that's how, and you may also have fluorescence back here. And actually from experiment, now you can determine with some other, so it usually goes to some higher levels, some vibronic structure and things, but comes back at a lower energy. So you put the green light, the red light goes back. So that's what it is, and it's a triplet state, so it is total spin 1. And I don't know, shall we, so for me, for example, what was interesting, people also talk about zero field splitting. Right? So actually, that's a triplet state, and we discussed with you that you have 2 electrons now in the ground state occupying this quadrivalent space on 3 carbon atoms. So there are 2 electrons at each point experiencing electron repulsion. So the electron repulsion is one thing, but from the spin point of view, you have term in the Hamiltonian like dipole-dipole interaction. 2 spins interacting through space. So now I'm talking about spin, only spin component. And normally you have this form of, we can talk about this, why it looks like that. Actually, for spin 1, you can say spin 1 is already 2/3 right away, minus 2/3. So basically, you have SZ can be projection either +1, you can have 0 or -1. And you can see that energy of plus and -1 will be equal because you take SZ squared, 1 squared is 1 minus 2/3 is D divided by 3. And D is this term which is responsible for dipole-dipole interaction. And energy corresponding to the zeros projection is going to be 0 minus 2/3, so minus 2D divided by 3. So basically, in reality, but we are talking about this dipole-dipole interaction, so it's actually way smaller energies than this energy. Some energies nearer here. So that means what I'm trying to say that in reality, even this state, the 2, 3, in reality is actually split into 2 levels in 1 level, corresponding to different projections of electron spin. So we call it ms equal to 0. This is ms equal to plus minus 1. And we know that this equals to how much? 2.8 gigahertz.
Do you know the exact number?
Because for this whole technology, you need to know that number because the whole fuss is about this. And actually in E3, you're going to have the same splitting. It's also triplet. Here is how much? So let's check with our logic. Does it even make sense? So how do you remember how D looks like, the parameter D? So let's remove this single states for now. So it already kind of makes sense to me. So here, two electrons on average spend time closer to each other than here. The same two electrons, but they're more spread in space. So their distance on average is further away. So the dipole-dipole interaction is a little smaller. So this D will be bigger here than there. But we can even estimate that. So D is normally, you have gamma electron, because it's two electrons, it's just squared. And if we take units of hertz, H bar without bar, H divided by R cubed. We actually can kind of estimate it from this value, because there's also this generally parameter 3 cosine square theta minus 1 divided by 2, actually. And this theta is counted basically between, so first electron, then second electron, and this is orientation of your magnetic field. So it depends on how electrons are located in space. So here, basically, let's say the field is along this axis. So theta is 90 degrees. You put theta 90 degrees minus 1/2. If here you can actually have all orientations, but you have that component which is basically 0. So you have 3 minus 1, like 1. So you're gonna be, this is estimation in between 1/2 and 1. So let's just estimate. I basically estimated at home. So from here, from these values of D, so you know that this is basically your delta is equal to D. Okay? If positive is plus D divided by 3. This is minus 2/3 D. So gap is actually D, right? So if you know it's 2.9 gigahertz, you put it here, then you can estimate average distance between electrons. Oh wow. Really? Tornado. Okay, maybe we should finish on this. No. But I think I found this is on the order like 4.5 angstrom or something like that.
I think you lost me in this part after.
But because it's a little bit magnetic resonance part, I didn't talk about these things before, right, in this class. But just to, for Joseph and in general, I was interested how to rationalize this, why it looks this way. Basically, because of dipole-dipole interactions of two electrons, and because of it's not spin 1 really, it's 2 spin 1/2, but we treat them as spin 1, and effectively we have that splitting them. All right, cool. Let me close it for here.